Hey everyone! In this video, we're going to take a look at an example where we're going to find the area under the graph of a function by using the lower sums. So to start with, let's read through the example. It says approximate the area under the graph of the function f of x is equal to x squared from 0 to 10 by using the lower sums. So why don't we graph this function right away so we can take a look at it and we can point out a couple of things. So the function x squared, this is your quadratic. So I'm just going to sketch our graph, and it's going to look something like this. And we want to find the area under that function. So this is y is equal to x squared. And we want to go from 0 to 10. So if I draw in the vertical line at x is equal to 10, the region that we want to find the area of is the one that's bounded by the graph of x squared, the vertical line x is equal to 10, and the x-axis. So this region here. And what I'd like to do is I'd like to approximate that area by using a couple different numbers of subintervals. So let's take a look at what happens when we use two subintervals, 5 and 10. So those will give us approximations of the area of this region. And then lastly, let's take a look at what happens as the number of subintervals becomes unbounded. Or in other words, as the number of subintervals increases to infinity. Now, one additional important thing we can point out right away, whenever we're using the lower sums, remember what that means is the height of the rectangles we're going to use, that's going to be the absolute minimum that occurs within each subinterval. Now, for this example, in my interval from 0 to 10, my function is increasing everywhere. Because it's increasing everywhere, that means within any subinterval I pick out, the absolute minimum is going to occur at the leftmost point within that interval. Because it's increasing, that leftmost point is the smallest possible value. Anything to the right of that is going to have a little bit of a bigger y value. So that makes it easy for picking out these lower sums because we can easily identify where that absolute minimum is going to occur. So let's start by taking a look at two subintervals. So if we're going to use two subintervals, that means we're going to take our interval from 0 to 10 and we're going to split it into two pieces, from 0 to 5 and from 5 to 10. So on the graph, what this is going to look like, we have from 0 to 5, and then our second piece is going to be from 5 to 10. And we're going to split it up, so we're going to use two rectangles in this case. And we're going to find the area of both those rectangles, and we'll add them together in a sum, which will give us an approximation for the area. So to do this, we need two things. We need to know the width of each rectangle, and we need to know the height of each rectangle. The width of the rectangle, or delta x, or the change in x, we can find that by taking the width of the entire interval and dividing it by the number of subintervals we're using. So 10 minus 0, so that gives me the entire width of the interval we're looking at, and we want to cut that into two pieces. So each of our rectangles is going to have a width of 5. And then the second thing, the height of each rectangle, which we're going to notate as f of c of I, because these are going to be points that are on our function, and because we're using the lower sums, we want these to be the absolute minimum within each subinterval. And as we discussed, because x squared is increasing everywhere between 0 and 10, the absolute minimum in each subinterval is going to occur at the leftmost point. So for the first subinterval from 0 to 5, the leftmost point is going to be at 0. And then our second interval from 5 to 10, the leftmost point is going to be at 5. So then the area, or the approximation of our area, let's use our summation notation. So the sum of two rectangles, this is going to be equal to the sum. So here we have capital sigma, which notates the sum. We're going to start at I is equal to 1. We're going to go up to 2. And we're going to take the height of each rectangle, and we're going to multiply it by the width of each rectangle. So f of c sub I, this indicates the height of every rectangle. Delta x, this indicates the width of each rectangle. And this is actually a constant because every rectangle has the same width. So if we expand this out, our first rectangle has a height of f of 0, and it has a width of 5. Plus our second rectangle has a height of f of 5, and this also has a width of 5. So if we evaluate f of 0, so remember our function f of x is equal to x squared. So f of 0 is 0. F of 5 times 5 is 25. So our approximation, 0 times 5 is 0, plus 25 times 5, our approximation is 125 square units. If we draw this in, the first rectangle we found actually has a height of 0. So in this first interval, we actually don't have a rectangle there at all. In the second interval, the height is up at f of 5, so this is a height of 25. If we draw in that rectangle, it'll have a height and it bumps up right against the function at that point. So this point here is the point 5 and 25. So the area of this rectangle is 125, and that's our approximation. But as you can see, if I draw in our other boundary here at x is equal to 10, we have a lot of area that's missing. So we have a lot of error. So this isn't a very good approximation. But it's our first one using 2 subintervals. And next, let's increase that to 5 subintervals. So we're going to go through the same process, but now we're using more subintervals. So in this case, we're going to take our 0 to 10, and we're going to split it up into 5 pieces. So we have the interval from 0 to 2. We have 2 to 4, 4 to 6, 6 to 8, and our last subinterval is from 8 to 10. And as we said in the last one, each of these subintervals, there's going to be a rectangle there. So to find the area, to approximate the area, we need 2 things. We need the width of the rectangle, and we need the height. So the width, delta x, if we take the length of the entire subinterval, divide it into the number of subintervals we're using. So in this case, each rectangle is going to have a width of 2. And now for the height of each rectangle, again, we're using f of c sub I to indicate that. Just like the last one, this needs to be the absolute minimum within each subinterval. And the absolute minimum is going to happen at the leftmost point. So we have f of 0, f of 2. 2 is the leftmost point in that second one. We have f of 4, f of 6, and finally f of 8. So our sum of 5 rectangles, again, we'll use our sigma notation for the sum. So we're starting at 1, we're going to go up to 5. F of c sub I, each one of those indicates the height of the rectangle, times delta x, which indicates the width of the rectangle. And if we expand this out, so our first rectangle is going to have a height at f of 0, and the width is 2. And our second one is going to have a height of f of 2, also with the width of 2. And then if I just keep going here, f of 6 times 2, and f of 8 times 2. So our function again was just x squared. So our first one, f of 0 is 0. So just like we saw in the last one with 2 subintervals, that very first rectangle actually doesn't have a height, so we don't have a rectangle there at all. Our second rectangle is going to have a height of 2 squared, which is 4. The third rectangle has a height of 4 squared, which is 16. 6 squared, which is 36, so the height of that fourth rectangle. Then our last one, 8 squared, is 64, and that's the height of the fifth rectangle. So we have 0 plus 8 plus 16 times 2 is 32, plus 36 times 2 is 72, plus 64 times 2 is 128. And summing these all together, we get a total of 240. Our last one, we had a sum of 125, so this is increasing, so we're getting a little bit better. And now let's take a look at what this would look like. And now let's just take a look to see what this would look like. So we have width of 2 in each case. So our subintervals are from 0 to 2, 2 to 4, 4 to 6, 6 to 8, and 8 to 10. And now if we draw in our rectangles, as I said, the first rectangle actually doesn't have a height, but our second one from 2 to 4 has a height of 4. The third rectangle has a height of f of 4, so that's a height of 16. The fourth one has a height of 36, and our last one has a height of 64. And just like the last example, with two subintervals, we can see that we still have quite a bit of missing area. So we still have quite a bit of error here, but maybe if we use more rectangles, we'll get even closer. So let's jump up to 10 subintervals. Now, in this case, our subintervals are going to be from 0 to 1, 1 to 2, 2 to 3, and so on. And then our rectangles, the width of each rectangle is going to be the entire length divided by the number of subintervals. So that's going to be 10 divided by 10, so each rectangle has a width of 1. And then the height of each of these rectangles is going to be at the leftmost point, so f of 0, f of 1, and so on, all the way up to f of 9. Our last subinterval is from 9 to 10. The leftmost point there is 9. So our sum of 10 rectangles, so sigma, and then we'll start at 1, and we're going to go up to 10, of f of c of I, so each height of the rectangle times the width of each rectangle. So we have f of 0 times 1, plus f of 1 times 1, plus f of 2 times 1, and so on. And our last rectangle will be f of 9, which also has a width of 1. And so because our function was just f of x is equal to x squared, and in each case we're just multiplying by 1, each of these terms is going to be the perfect square. So f of 0, 0 squared is 0, 1 squared, 2 squared is 4, 3 squared is 9, and we're going all the way up to 9 squared, which is 81. So we're adding the perfect squares here. And if we do that sum, if I add all those up, we get an approximation of the area of 285. So again, it's still increasing and we're getting closer. And now if we take a look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I draw this out, if we take a look at these rectangles, some of these are going to be pretty small. But just as we saw as going from 2 subintervals to 5 subintervals, the error, the missing area, did decrease. And now that we're going up to 10 subintervals, it's decreasing even more. So I'm just putting these in, not being super accurate. But as you can see, that error, the space that's in between our function and our rectangles, is getting smaller each time. So that just goes to show that as we increase the number of subintervals, the approximation for our area is getting closer and closer to what the actual area is. Now, lastly, Let's take a look and see what happens as we increase the number of subintervals to infinity. All right, so now as n becomes unbounded, or the number of subintervals increases, we are going to split up 0 to 10 in a bunch of subintervals. So we have x sub 0 to x sub 1, we have x1 to x2, and we'll go all the way up to the subinterval of x n minus 1 and x sub n. In this case, x sub 0, this will be at 0, and x sub n, this will be at 10. So they're all going to have the same width, but we have an infinite number of them. And to find the area of each rectangle within each of these subintervals, we need the same things as last time. So we need to know the width of each rectangle. So I'll take the width of the entire interval, and I'll divide it by the number of rectangles we have, which in this case is n. All right, now the next thing, let's think about the height of each of these rectangles. So we need to know the x value where the absolute minimum is going to occur. So c sub I is the way we notate that. All right, now the second thing, let's think about the height of each of these rectangles. So to do that, let's first think about where the x value on where that height is going to occur. Because we're using the lower sums, and because our function is increasing everywhere in our interval, the absolute minimum is going to occur at the leftmost point within that interval. So if I just draw in a couple of these x values, x1, x2, x3, the spacing in between each of these x values is going to be 10 over n. Now, when I start with I is equal to 1, that indicates my first subinterval, but I don't want the x value x1, I actually want the x value x sub 0, because that's the leftmost point. So for this first interval from 0 to x sub 1, I actually want to use this point, x sub 0, as the height of that rectangle. If I go to the second interval, that would be when I is 2. I don't want x sub 2 for that height. I actually want x sub 1. So I actually want this point here. And then that width, again here, this is also 10 over x. So we can generalize each of these x values as 10 over n. So that's the width. So that's how far along I'm moving. And I'm going to multiply that by how far I need to go. So because we want the leftmost one, I'm going to do I minus 1. If I were just using I, that would give me the right-hand side of each interval. So then if I subtract 1, that will get me back to the left-hand side. So that means f of c sub I is f of 10 over n times I minus 1. Which, since our function is x squared, this is going to be 10 over n times I minus 1, and all of that is squared. Now, to work with this, I'm actually going to simplify that further. So we can square each part in here. 10 over n squared is 100 over n squared. And if I take I minus 1 and square that, we have I squared minus 2I plus 1. Now for each I value, so for 1 all the way up to n, if we plug that in here, this will tell me what the height of each rectangle is. Okay, so we know the width of each rectangle. We know each rectangle is 10 over n units wide, and we have a way to calculate the height of each rectangle. So now we can take all of that and we can plug that into our sum to find our area. So do S sub n, since we're using n rectangles, and then we're going to have sigma. We're starting at I is equal to 1, and we're going all the way up to n. And we have f of c sub I, this represents the height of each rectangle, times delta x, which represents the width of each rectangle. So if I plug in what we already figured out, f of c sub I is 100 over n squared times I squared minus 2I plus 1. And then this is all being multiplied by the change in x, which is 10 over n. All right, so now from here, we're going to use some of our summation properties to help us simplify this. So one of them is any constant within a sum, we can actually bring that out front. So 100 over n squared and 10 over n, these are both constants because n is going to be some fixed number, what's becoming unbounded. So I can actually bring that out front. And if I multiply those together, we have 1,000 over n cubed. And then that's going to leave within our sum, we just have I squared minus 2I plus 1. Now, the next property for sums that we can use is addition and subtraction. We can actually split that up. So this will stay out front, the 1,000 over n cubed. And now we'll split this up so each term here will have its own summation. So we have from I is equal to 1 to n of I squared. Then minus, here's another constant, the 2, so let's bring that out front. And then we have another summation, I is equal to 1 to n of just I. And then lastly, we have the summation from I is equal to 1 to n of 1. Now that we have this all split up and simplified a little bit, each one of these, there's a special rule, special shortcut for each of those summations. So for that first one, the summation from 1 to n of I squared, what this works out to be is n times n plus 1 times 2n plus 1 all over 6. In the second one, the summation from 1 to n of just I, that works out to be n times n plus 1 over 2. And then the last one, this is just a constant, so this ends up being just n. All right, so now let's do a little bit of algebra, and we'll simplify this big expression. So the first thing I'm going to do, within my brackets, that first term, I'm going to multiply this all out. If we do that, we end up with 2n cubed plus 3n squared plus n, and that's all over 6. In my second term, the 2 and the 2 in the denominator will simplify. So we just have minus n squared and minus n. And then we have our plus n here. So if we keep simplifying, the 1,000 over n cubed is still hanging out front. We have 2n cubed plus 3n squared plus n all over 6. We have a positive and a negative n, which will simplify. And then I'm going to get a common denominator, so we have minus 6n squared over 6. Now let's bring those two terms together. So combining those together, we end up with this fraction. So we have our 1,000 over n cubed times 2n cubed minus 3n squared plus n all over 6. And now what I can do is distribute this 1,000 over n cubed to each of these terms. So if I think about each of these over 6, we can do a little bit more simplifying. So we distribute to the first one, n cubed on top and bottom will simplify. So we just end up with 1,000 over 3. So if I distribute this, the second part then, we have an n squared on top and an n cubed on bottom. And then, so 2 of those will simplify. So this will end up over n. And then we have 1,000 times negative 3 over 6. That all simplifies to 500. And then our last term, we have an n in the numerator, n cubed in the denominator. So this will be plus, we'll end up with an n squared here. And then 1,000 over 6 will simplify to 500 over 3. So using some of our summation properties, we're able to get this down to this point, 1,000 over 3 minus 500 over n plus 500 over 3n squared. And now what we want to do, so this expression represents the area of all those rectangles added together. And now we want to let n become unbounded. So what we want to find is we want to find the limit as n approaches infinity of our sum. So the limit as n approaches infinity of 1,000 over 3 minus 500 over n plus 500 over 3n squared. We could do this with any number for n. We could do this with 2 or 5 or 10. And if we plug those values in, that would give us the areas that we saw in the previous parts of this example. But now we want to let n become unbounded. So if we evaluate this limit, 500 over a really big number, this is going to approach 0. 500 over 3 times a really big number, this term will also approach 0. So that means the area under this curve is 1,000 divided by 3, which is 333 and a third square units. And that is the exact area underneath this curve. So, as you can see, we started off with a very small number for n. We looked at 2 subintervals. We got an approximation that wasn't very good. We increased to 5 subintervals. Our approximation got a little better. We increased to 10. We ended up with an approximation for the area of 285, which was getting even better. The amount of error was reducing. But if we can let that number of subintervals become unbounded, if we can use an infinite number of rectangles, we can find the exact area, which we ended up here with 333 and a third square units.